This is the Lab 5 report of Faraday's law produced by Xin Yugong. In this lab, I'll go through the introduction and fundamental theorem, the experimental process and results, computational analysis, and the final evaluation of two what-if questions. This experiment examines the interaction between the falling magnet and the tube of aluminum foil, and model the interaction computationally, then compare it with the observation data. The fundamental principles applied in this lab are Newton's second and third law, Biot-Savart law, Lenz's law, and Faraday's law. The main process of the experiments are firstly, find the nth pole of the bar magnet. Then, with one hand, hold the tube vertically and position the magnet just above the top opening. Record a video on smartphone of the entire tube and drop the magnet through the tube. Then calculate the average time it took for the magnet to fall through the length of the tube, which from my calculation is 1.6 seconds. This is my computational model for the periscope analysis. In this part, I used the starter code and updated some of the initial conditions for the tube and the magnet. Other changes include, for example, calculate the magnetic field at the position R relative to the bar magnet, and for example, calculate the rate of change in the magnetic flux through each ring caused by the falling magnet. All of those functions utilize the fundamental principles introduced before. This is my result from my computational analysis. We can see that the time for the magnet to fall through the entire tube is 3.993 seconds. Here's my interpretation of the simulation. From the graph above, I can know that red is the counterclockwise and blue is the clockwise current, because the magnetic field is facing up and increasing before reaching the center of the tube, so produce a clockwise current. And when it passes the center of the tube, the magnetic field at the center is up but decreasing now, so produce a counterclockwise current. What happens to the dynamics of the system when you flip the magnet around? In this case, the time past the tube and the magnitude of induced magnetic field stays the same, but the direction of the current produced at any moment is flipped. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? The computational system will be more accurate as we can make sure the magnet does not fall in straight line nor collide with the cardboard, thus affect the induced current and the magnet's instant velocity in the tube. And the computational model can be made more accurate if we include the consideration of air resistance. What does the shape of velocity versus time plot tell you about the forces acting on the bar magnet? From the graph, we can see that the velocity decreased at the beginning of entering the tube. This means the induced force acts in the opposite direction of motion, until a point F net equals 0 inside the tube, such that the external force resulted from the coils counteracted the weight of magnet, so produced no external force and the terminal velocity. Here comes the section of what-if questions. For the first what-if question, the current will increase with a reduced resistivity, so create a stronger induced magnetic force on the magnet that acts in the opposite direction to its motion. So the magnet will fall slower before it reaches its terminal velocity. And for the second what-if question, with holes in tube, there will be less effective conductive rings that can produce current and magnetic force, so the magnet will fall more quickly. Thank you.